Alrighty. Okay, now we're recording. So basically the goal is we're just going to go through all of homework 3, which is going to be based on circuit reduction. And then I believe homework 4 is going to be a little more in line with what it is that we could expect on exam 1. Um, so finding the equivalent resistance seen by the independent source in the following circuit. The thing is that quiz 1 is just going to be based entirely on oh, David's coming in. Welcome to the call, David. Is David in? Hold on. We gotta go open this. All right, there we go. So quiz 1, as far as I am aware and have written down, is going to be on a circuit reduction, which is basically all of quiz 3. So if we have like a nice big independent source like this, we just kind of go down the line. This is a pretty straightforward one, which is nice. So we got 10 volts. It's going to be 6, 12, 9, 4, 7. Here I'm thinking of combining, just going to do a few steps in one here. So combining resistors in series. This is going to be 18. You just add them together. This will be 16. This will be 4. This is still 10 volts. Oh, geez. 10 volts. Now to combine these two in parallel, we got 1 over R equivalent is equal to 1 over 4 plus 1 over 16, which if I'm right, that's going to be 4 over 16 plus 1 over 16 for 1 over R total. So R total is going to be 16 over 5. Let me get a calculator for it. Where is it? There it is. It's probably going to be like 3 point something. 3.2. Nice. So 3.2. So resistor, 10 volts, 18, 3.2, which means that the total resistance of the circuit is going to be 21.2. Does anyone disagree with that? So equivalent resistance is going to be 21.2 ohms. We're going to save that. We'll check all the answers. The problem is the answers are all in one like little answer box there. Let's do the second one and then we'll figure it out here. All right. So this is an interesting one. Oh wait, it's a current source, which goes there. I'm gonna redraw this circuit a little bit. I'm gonna draw it like this instead. I'm gonna put all of these resistors like this. And then this is gonna be a resistor that goes like this. Ah, geez. Three milliamps, 4 kilo ohms. This is going to be 3, 5, 7, 10. So basically, my plan, I mean, it's the same thing. This shouldn't have too much of a difference just because it's a current source. You could still, this is going to be 15 ohms. That's basically all this right there. And then this side is going to be 10. This is going to be 4. Obviously, this is kilo ohms, but we're kind of ignoring that notation right now. notation only really matters if there's like a difference in notation, right? So if we had like 4 kilo ohms and or this was 3 kilo ohms and this was like just 5 ohms, that's a totally different it's a different thing, right? Anyway, 1 over R equivalent is equal to 1 over 10 plus 1 over 15. I'm just going to punch that into my calculator now. So this gives me 1 over R equivalent is equal to 1 over 6, which means that we get 6. Yeah, 4 and 6, meaning I'm going to estimate just already total resistance is going to be 10 kilo ohms. Any uh any disagreements? Do we have like a chat option? We do have a chat option. If you guys just want to drop any questions in the chat too, you can do that. Okay. We're going to check both of these answers. So let's just do it now. Let's see. So we got 21.2 and we got 10. 21.2 and we got 10. Boom. There we go. Let's see. Look, her notation is wrong on that answer. Wait a minute. Unless the 3 milliamps does play a role. Because it shouldn't though. Hold on. We have the answers here. Because I mean, it's just 3 milliamps. This is the first circuit. Okay, this is circuit number 2. Oh, I see. Wait, no, that's a different circuit. Hold on. Okay, yeah, we were right. 10 kilo ohms. She just had the wrong. This is going to be a trend, though. Just so you guys know, as you go through Ms. Fahim's notes, the discussion questions, the homework questions, there are mistakes that she has made that will be very frustrating to deal with. Anyway. Next question? No questions. I hate that we kind of got a spoiler for the other question where we're going to have to do why is this okay? Jesus. Oh, we're going right into we're going to crash right into a bunch of other work that we have done. Okay. Let's just throw this up here. Circuit number letter C. Okay. So we're going to have a 200 millivolt source right here. It's going to come down to a 500 ohm resistor, 400 ohm resistor, 600 ohm resistor, 300 ohm resistor. And then it's going to come over here. And this is what I was talking about earlier. This 1 point, I'm just gonna write this differently. I'm gonna say 1200 ohms. It's 1.2 kilo ohms. I'm just gonna keep it all as the same notation. That way we can more easily combine the different circuits. Okay. So we have 200 millivolts. Okay. So here's what I'm currently thinking. I will say I didn't get a good look at that the spoiler for how to do this question. So I see 500, I see 400. We're still gonna solve for that. So it's gonna be 300, 200 millivolts. So I'm gonna say 1 over 600 plus 1 over 1200. It's gonna be equal to 1 over R equivalent. So I'm just gonna do it quickly on the calculator. Let's see, plus 1/1200. So I'm gonna get, I have as my R equivalent value, I'm getting 400 ohms. Let's see. So I got 400. I don't see why we're gonna have to do a, why would you change this? 4, 8. Minus plus. So here's what I'm saying. Look, you have 800 right there. You have another 800. So I'm gonna go with 1600 ohms or 1.6 kilo ohms for C. Let's go. All right. Okay. Okay. I'll just write this. R. Geez. I don't know what the deal is when I like plug my laptop in to charge. Makes my stylus really glitchy. Okay. R total 1600. Okay. Let's just keep it going. This is going to be D. So this one is giving us a polarity for some odd reason. Oh. So this one, it says 12 volts, 6 kilo ohms, 4 kilo ohms, and this is going to be 0.5 VX. And VX is, that's this polarity. What the hell is VX? It just says VX like right here. What? Okay. So this might seem a little bit silly, but I'm working under the assumption right now that these two resistors are going to be in parallel. Because if you were to label these nodes, A, you have a node in here, B, C, 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 C. They share the same A to the C. So I'm going to redraw this. Let's see. Tell me if you guys agree with this. So we're going to have 1, 2. Oh, fuck. So this is the only thing I changed. Is the positioning of this resistor here. And we have A, we still have A all the way up here, like we have B all the way down here. We have, well, okay, I guess we're mixing up our nodes now, but whatever. So let's just combine those two resistors, right? So we got 1/3 plus 1/6 equals 1/R equivalent. So we're gonna have 1/3 plus 1/6. I'm gonna get 2 ohms is the R equivalent value. That's not our final answer though. So I'm getting plus minus. One of the things is that, oh fuck, I still don't know what VX. Maybe VX is the voltage across these resistors here, the polarity. there is what we're looking for. So 2 ohms. This should still be plus minus like that. We have 4K here, 0.5 VX. Now, I could be wrong. I'm still shooting from the hip on this one. Part of me wants to KVL this. So I'm gonna do a KVL maybe like this on the outside. See what happens. This could be wrong, but let's see what our approach is. So you have 12-volt rise minus 2. We're gonna assume current flow. So I'm gonna assume current flowing like that, and then this is going positive to negative. 2 minus, I'm just gonna say IX. IX. This current over here will be IY. And that's gonna equal 0. So if we know IX, which in this case, it's looking like it's going to be 6 amps. I got this by, actually, I'll just do all the math for it. Negative 2 IX is equal to negative 12. IX is equal to 6 amps. We can find the voltage across this resistor with V equaling IR. So that's going to be, well, 12 volts. 6 times 2. So I'm gonna assume this is our VX value, meaning that I'm gonna also assume that this voltage dependent voltage source is going to be outputting 6 volts, is my assumption. Holy hell, I don't know where I'm going with this.
Could you try
Yeah.
KVL on the other loop?
Are you thinking something like this, maybe?
I'm on the other loop.
Like this? Oh. We could do that. Let's do that. Yeah, KVL. Okay. So let's KVL this like that. Oh, Danielle's coming in. Come on in, Danielle. Welcome to the call, Danielle. Daniel. Currently working on
Hello.
letter D. Hey, we're working on letter D from the homework 3 right now.
Very exciting.
Yep. It really makes me enjoy my time here at UCF. I'll put this over here. Alrighty. Okay. Let's see what we got. KVL, 12-volt rise. And then this, I'm going to assume plus, this will be plus minus here. So then we'll have plus 4K IY minus 6 is equal to 0. So then this is going to be 4K IY is equal to negative 6, meaning that IY is equal to, again, negative 6 over 4K. Okay, so we found all the currents. I don't really know what the hell we can do with that. Let's just see her breakdown in the notes here. See what we got. Oh, really? Lovely.
Is this your first time taking the course?
No, this is my second time actually taking the course. I got a C minus the first time going through, so that grudge helps me study.
Oh,
for
shit.
this. Yeah.
Yeah, because I'm like, oh, damn, you know what's up.
It-
But like, not that you can't know what's happening, just your first time around, but I'm just curious.
it definitely takes like it's a lot to take in. This
Mhm.
course moves pretty quick. So
Yeah.
Okay, so let's see what we got. It looks like we were right here. So they were in parallel. We did get a 2 kilo ohm. Oh, wait a minute. Wait a minute. Because our calculation here was 12 volts. Where our mistake was this is not 6 amps. My calculation, I just punched in, where did I get 6? This right here. This resistance value here, the 2, this should have been 2 kilo ohms. So that would just be 2 times 10 to the 3, I believe. Ohms of resistance. Let me make sure I have my powers of 10 correct.
If everything is in the same unit, is it important to account for it like that? Like, can you just be like 2 kilo ohms?
In this case, it is because you're going to be combining two different measurements that are in different units. So that's why this right here,
Got you.
in earlier questions, we did basic circuit reduction, and I just really ignored the units up until the end. And we got away with it pretty well, just because there wasn't really anything else coming into play with it. With
Mhm.
this circuit, we just reduced the resistors. So as you can see, I just have 6, 12, 9, 4, 7. And then I just simplified it all. And then I said, okay, that's 21.2. And then in the second one, you see, I kind of wrote for some of them, they were kilo ohms here and here. But then I
Mm,
got bored of it. And then I just gave up on writing it. And then I wrote 10 and 7. But all the resistors are in the same unit value. So that's why at the end, I can just say, hey, 10 kilo ohms.
right.
What sets this question apart is that I do Ohm's law. So we were on the right track actually. So my mistake was that this notation right here, this -2 ix, this should have been -2 here. This should have been written kind of like this. Instead of -2, it should have been -2 times 10 to the -3, or fucking -3, Jesus, just 3. That way, when I divide -12 by this value, this is not going to be 6 amps. It's going to be 6 milliamps. That changes a lot because 6 amps is a hell of a lot of current that you're going to have to deal with. 6 milliamps is totally different, you know?
Okay. So because our voltage is in a different it's not in like the basic, like if we had like kilovolts, is that even a thing?
Yeah, that is a thing. 12
But
kilovolts.
if it wasn't kilovolts, like we could leave it and then it would just be 6 amps or kiloamps or something.
I wouldn't you okay, you would get the right answer that you're looking for, because here's the thing, if this was 12 kV kilovolts, what you would have is that would change this to ix is equal to, let's say, -12 times 10 to the 3 divided by -2 times 10 to the 3. So these 10s would cancel out and you'd end up with 6 amps.
Mm,
Right. But that would just because it's convenient. Because imagine if I said to you, oh, this is actually going to be 12 megavolts. If I said it was a megavolt, right? For example, this would change to 10 to the 6. And then that would change this answer to be 6 times 10 to the 3 amps, I believe. So the thing is, in the earlier questions, circuits A through C, we weren't messing around with the voltage source at all. So here, all I did was reduce, and then I just 4 plus 6, that's 10. And then I'm like, oh wait, the notation's kilo ohms, But in this case, we did reduce, and we can actually see a little bit of that work that we did here. So here I said, oh yeah, 1/3 plus 1/6. That's these two resistors right here. And then and this is where my mistake was, because I just wrote 2 ohms. This should have been 2 kilo ohms,
mm,
which changes everything. That changes a lot.
right.
So let's see. So how does that change things here? So now that we do Ohm's law, right? So this 12 volts, this becomes 6 milliamps. We KVL'd. Where the hell does this VX come from? Oh. So it goes VX minus 4. Oh, okay. So what they did was they took this original circuit here. Move this over here. This is really, this zoom is neat, but this is in the way. Okay, whatever. So what they did was they did a KVL like this. That's what they did. So this KVL, so it looks like this VX, we were confused as for what it pertained to earlier. It looks like it pertains to the voltage kind of across here. So
Oh,
if
after
we're-
you simplified it.
yeah, well, this is, we're going back
Oh,
to the
okay, I see what
original
you mean.
circuit here, actually. So this
Gotcha.
is going to be plus VX. Then we're going to go down here. So we're going to go, we're going to assume the signs here. I'm going to go positive, negative like this. So we're going to keep it in the right flow. So this is going to be minus 4 kilo ohms times, we're going to say IY like we had earlier. And then we're going to say minus 0.5 VX. And then that's it. And that's going to equal to 0. So in this case, we actually have two variables. So if we simplify this, we get negative 4 kilo ohms IY plus 0.5 VX equals 0. The reason I got plus 0.5 is because I combined both of these.
Hmm.
Then we're going to look at this back here and we're going to say, okay, well, let's try to get rid of this IX here. So we know that we have a current flowing here. And let's say we have a current flowing. How did they do the notation here? I1. God dang. Okay. We're going to go like this. Current's flowing that way. Jesus, this is a nasty mess. Okay. Current flowing that way. Current flowing down. And then we're going to say current flowing in there.
Be right back.
Go for it. So this is going to be I1. This one's going to be I2. Or no, it's just so we could keep it all consistent. IY. And then this will be IX. So this is going to be I1 is equal to IY plus IX. Oh, Fank has entered the waiting room. Let's let Fank back in there. Welcome to
Go
the call,
away,
Fank.
Fank.
Yeah. Okay, so we've got
He almost didn't let you in. I had to beg
What
him.
the heck? Why? Oh my god.
God dang. Okay, so we know this is 6 milliamps flowing out here. So, how do they get 1.5? I2 is 1.5. Is that because of the oh, I'm missing something here. six divide. Okay, I have a theory. This is gonna be my theory. It seems to work. So let's see. So some of you guys weren't here for that, but we had calculated. Uh. Dang, okay. So equivalent resistance here was 2 kilo ohms. That means this is 6 milliamps. Okay. Times the equivalent resistance here. The resistance is 2 kilo ohms. And then the current flowing through this resistor right here is 6 milliamps. So this is just 6 times 10 to the negative 3, and then 2 times 10 to the negative 3. Is that still going to give us the same? Holy, oh wait. Oh wait, not negative 3. Hold on, this is just 3. Yeah. That's why. Aha, okay. Voltage. Voltage equals 12 volts. The voltage across this resistor is 12. Meaning that Vx is 12. My reasoning is because we have Vx here. These two resistors are in parallel. That's why we were able to combine them right there. Now, one of the things you want to keep in mind is that resistors that are in parallel have different currents flowing through them, assuming that they have different resistance values. But no matter what the resistance value is, they should have the same voltage across them, right? So, for example, if I have two resistors and I have, I don't know, 10 ohms, and then this is going to be 2 ohms, and then they're connected to a 12-volt battery source here. When it whatever flows around, you're gonna have 12 volts of well, it's a potential voltage at both of the resistors, although you'll have different currents flowing through each of the resistors because of just the nature of the resistance.
Right.
So my assumption, this is where my hypothesis comes from. Vx is 12. So I'm gonna put 0.5 times 12 equals 0. We get negative 4 kilo ohms. Y is what that's supposed to. That's so messy. God damn. 4 kilo ohms. So this over here is going to be 6. And you have negative 4 k ohms IY. So let's do negative 6, negative 4 kilo ohms IY. So that's going to be 1.5. This is going to be milliamps because keep in mind you have kilo ohms. So when you divide negative 6 by negative 4 times 10 to the power of 3, you get milliamps. And that's going to be your IY. So
Okay.
So what's going to happen is this is our answer for I1 is going to equal 6 plus 1.5, and this is all in milliamps. So I1 is going to equal 7.5 milliamps, just like she has it here. And what that means is then I guess she just plugs it into Ohm's law. So then, I'm V equals IR. So we can say, hey, this is our total current flowing through the whole thing. We have our total voltage in a sense, or not so much our total voltage, but the voltage through the resistors. So we can say resistance is equal to voltage over current. So we have our most important measurements. So this is going to be 12 volts over 7.5 milliamps. And so then when I plug in 12 over 7.5 times 10 to the negative 3, we get 1600 ohms or 1.6 kilo ohms.
Hey,
Oh, ah, that's exhausting. Okay, did that make sense? I know I was going a little fast on it. I feel like I
yeah,
was
I
a little
came
all
in
over.
on like the final leg of this, but it seemed like you were reasoning through it like pretty clearly, and it was good that you caught the mistake and were able to backtrack and didn't get too overwhelmed by it. So good stuff.
Yeah, this one was a tricky one, that's for sure. Hopefully it's not on the quiz. All
So,
right, go
okay,
ahead.
I want you to like reason with me on something.
Okay.
Why are we going to reduce or simplify a circuit? Like, let's say we have a parallel circuit and we want to find the voltage on this parallel circuit. That's fine. And it's fair play to reduce it because it'll make it easier to find the voltage. And we know the voltage across every single resistor is going to be the same. But then it'll ask for a current along a single resistor. So you
Mhm.
simplify it, you find the voltage, and then it makes sense that we're backtracking to find the current along one single resistor. That was a question.
Okay. Okay. Let me make sure I understood your question correctly. Um, so when it comes to finding the currents through this circuit, um,
It's like,
I
why are
think
we simplifying it to just like expand it again? That's what I'm curious about.
okay, so we simplified it for the reason of finding VX. So one of the things is that let me kind of like draw this a little more neatly down here a second time, just because when it's messy, I can't focus when it's messy, right? So we have this is our original circuit here. Um, Come on, my laptop wants to cooperate here. Let me unplug it for now. It gets glitchy when I plug it in for some reason. I don't know why. But anyway, we have these here. So what we have understood so far is that here we have, this is our 3. So if you look over here, this actually has it written a lot better. Oh, can you see that on the stream over here? I'm like highlighting it.
Yes, the VX.
So this VX here um is responsible for
The
kilovolts.
voltage
It's the voltage
across
across
both
that
of
resistor.
those.
Well, it's the voltage across this resistor. I actually did it a bit of a different way than how she did it. So she found the voltage by how the fuck did she find the voltage?
Did she do a KVL?
Yeah, and in a way, I guess she did. Yeah. Okay. Yeah. Actually, yeah. This is another thing you'll find a lot on her notes. She will like. She's writing this right here. She says KVL VAB equals 12 equals VX. She writes that like it's nothing. There's a lot of math behind that.
Right, like the
Um,
whole intuition is just
which
like,
yeah, which we did here. So this is what we did above, right? So we have the circuit. Now, what we recognize is that this resistor and this resistor are both in parallel, right? And what that means is that
or
what
we
that
could say
means
the
is that
3 kilo ohm one and the 4 kilo ohm one is in series. Is that true that they're in series? And could you simplify it from
no,
that
those would
point?
not be in series.
Oh, because they're not connected to the same node.
When resistors are in series, think of it like they have the same current flowing through them, right? In this case, they wouldn't, right? Because if if we have a current flowing here, the current is flowing through here, and through there. That is not the same current, right?
And if it's flowing in the other direction, that doesn't even make sense to consider.
No, these are not in series by any means.
Okay.
Yeah. Okay, so the way we did this was a little bit messier, I think. Uh, how did we do this? That's right. Okay, so what we did
Do we
was
want to start a new problem?
yeah, we could do a new problem. Let's see. Let's look at the next one. Find the currents. Oh, okay, we could, that's not too terrible, I guess. But this one isn't answering our voltage question. Basically here, we could look. I could race through it quickly. The way that
Whatever
we
you're
had,
comfortable with.
yeah, no, of course. The way we did this was, we had 12. Just want to make sure I have the right values here. Alright. Because it was a little messy, that is true. Okay. Okay, so here's how we did it. Which I don't know if this is how Miss Fahim did it when she did this through here, because I'm gonna assume you can also do this. This is the simple way is how I think she did it originally. So she probably KVL'd just the outside like this, right? That's my assumption. So if I do that, I get a 12-volt rise. Minus 3 times IX here. We're gonna say we have a current here. This is current IX. This is current IY. And this is just current I. 12, 3IX, and then that's equal to 0. Now, I want to make sure I don't make a mistake here. This -3 is kilo ohms. So I'm going to say -3 kilo ohms IX is equal to 12 volts. So what happens is when I divide this IX, I'm going to get 12 volts divided by -3 kilo ohms, and that's going to give me 6 milliamps. That's my current.
Mhm.
Was I frozen? Because I just like glanced over and all like it looked like it was
No, you're
frozen.
good.
Okay. Now, one of the things is that to find the equivalent resistance, what we did, so because these two are in parallel, we combined them. If you combine them, you get a circuit similar to this.
Okay.
Hold on. There we go. That's 12 volts. This is 4. This is 0.5 VX. And then this is going to be, this ends up being 2 kilo ohms.
So let's say
So-
that there was,
Go ahead.
sorry, excuse me. Let's say that there was another resistor underneath the dependent voltage source. So would that mean that that would also be in parallel with the 6 kilo ohm resistor and 3 kilo ohm resistor because they're both connected to one of the same nodes, or do they have to be connected to the both ends of the terminal?
No, it has to be both. It has to be
Okay.
both. Yeah.
Gotcha.
Yeah, which is also why, for example, the 4 kilo ohm resistor is not in parallel either. Because between these two, there's a node right there.
Gotcha.
Yeah. It's crazy how this all works here. So let's see. So the VAB. So here's the thing, right? At this point, let's label our nodes again. Right. So we have A, and then we have B, 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 and then we're just gonna make this node in the middle. We're gonna make that C. So in a way, this is my reasoning behind it. Right. This is my logic. Is that these, imagine these like circuit elements. Remember, like at the beginning of the semester, kind of we had these like rectangles and the
Yeah.
12-volt voltage source. I'm seeing this as being no, let's actually not even delve too deep into comparisons. Basically, what I ended up doing was, this is the equation that I ended up doing. I grabbed the 6 milliamp current, and then I multiplied that by the combined 2 kilo ohm voltage resistance, which is odd because
Oh, to find V, that is interesting.
Yeah,
Oh, but it's since it's the
because
same voltage.
it's the same voltage, but my question is,
You're a creative person for that.
why, yeah, what the, it's because we were working off of. Well, let me look at this. Yeah, no, this is all good, the way we did it here. We KVL, what we did it, okay, the way we did it, we simplified the circuit first, so we got the 2 kilo ohm resistor. We KVL'd that, so this is where our KVL equation is showing here. So then we have the 12 volt minus the 2 kilo ohm times the IX. Move the 12 over, divide by -2 times 10 to the 3. That gives us the 6 milliamps that we need. And that is the amperage that is flowing through this resistor, which is a combination of the two resistors, keep in mind. Now, what we did then is we said, okay, well, because this is nodes A up here and this is nodes B, we can plug in, you know, and this was a resistor in parallel. We know that if here, let me scroll up a little bit. If this has voltage Vx across it right here, then this over here should also have voltage Vx across it because they're in parallel, right? So with that knowledge, that's when we ended up saying, okay, so the current is flowing through this resistor. We know that resistor is going to have voltage Vx. So then we can say, okay, that's when we plug it in down here. The current times the resistance, and that gives us the voltage. And then to find the equivalent resistance, that's something that we needed to look at the greater image of the circuit. So that's why we ended up jumping back up to this unsimplified circuit, because the goal was, what is the resistance of the whole circuit, not just these two resistors that we combined, which is why we do a second KVL where we did a KVL of this part here, showing the 4 kilo ohm and the voltage dependent source. Because what we wanted was, we wanted to find the total current flowing through the whole thing. And then we also wanted to find, no, that's all we needed, because we know the total voltage, you know, the kind of the voltage is 12 volts. Now all we needed was the total amperage. That way we could divide those two and get, this is a total resistance of the circuit. That's why. Okay. Sorry, I talked through it and then I like felt like I understood it a little more the second time I explained it.
No, that's what it's all about though. That's
Yeah.
good.
And also, here's one thing. I'll like save this as a PDF and like send it in the chat afterwards too. That way we can, Choma, that way you guys can look over it. So I'm gonna erase this because I feel like this is just gonna add confusion to it. Let's just stick
I'm
to
gonna
the-
send this out because I'm actually in a different class. So I'm gonna.
Oh, fair.
How much longer do you think you're gonna be here for?
I think I'm just gonna do probably like two more questions. I have another call. I'm gonna do another call tomorrow at 7 again, so we could do a little bit more. And then I was planning doing an in-person on Monday around 12, just to study for the exam and the quiz.
Alrighty, nice.
Yeah. Yeah, and if you want to send an invite link to this Discord to other people, feel free to. I don't know if you here, I could
Okay, yeah, for sure. Can you send me the link to the Discord?
yeah, I'll drop it. Right.
I'll send the
There's
one
the
I'm
little
in.
chat
now.
box.
Wait, do we have the same professor?
Yeah, Fahim.
I have Dr. Nas.
Oh,
Fahim,
Dr.
yes, I have him.
Nas.
Did we take quiz 2?
Quiz 2's on Tuesday. That's what
Thank
that's what this
God.
all is.
Okay. Dude, I thought I missed it last week. I had to skip.
Oh, you're
wait,
good.
wait, so the circuit reduction stuff is super easy. We have to do circuit reduction with the extra voltage independent source, or the dependent source, I meant.
And like solving other things.
Circuit
Yeah,
D
yeah.
is
Talking about circuit D, yeah, this is so far what I'm seeing here, homework 3 is based mostly on. Well,
Or
okay, problem 1, problem 4. Problem 5, you might actually see a question kind of like this, if I'm honest. You know, this is a question that I could see us getting.
I mean, just redraw it and then we're
Yeah.
good.
This one's actually like really easy. With this, let's zoom this in a little bit.
You don't think that they would ask us to find like the voltage of anything or the current? They just want us to simplify it for this quiz.
They could either ask us to that's why I'm like just kind of practicing all of this. I remember us like focusing a lot on the idea, which one was it? Of this one of having like branches like this or shorts. But then
Mm,
also like I wouldn't be surprised if they had us doing a question similar, at least Fahim having us do a question like D, which was this one. Just because that one really tests everything that you're
Right.
Practicing on it. So okay, let's do one more and then we could because we've been going at this for an hour. That's crazy. Holy smokes. Okay.
You get consumed.
There's no better way than I would. This right here is how I love spending Saturday nights. You know,
Mm.
Jeez.
Can't go
There's
wrong.
nothing else I'd rather be doing. Okay, let's skip over this question. We'll find the other circuit. Find the
And
equivalent.
your name is
resistance.
Miguel?
Yeah, that's me. I'm also
It's nice to meet
WiseX on the
you.
Discord. Yeah, nice to meet you too. I'm telling you, I do study groups probably about every week just because I feel like having taken this class before, like I've seen how it can ramp up. And so I don't want to get caught in the wake this time around, basically. You know.
Fair.
So anyway, let's do this one, shall we? So let's see what we got. Find the equivalent
Let's go quick.
resistance seen by the source. Do we get? We don't get any numbers, but okay. So this is actually a really great example of what it is to what's the term? To identify what is in parallel and what is in series and what is well, okay, actually I don't think there's any other combinations of resistors that you can have.
Yeah, those are
Okay.
enough.
I think that's about it. I don't think there's any other ones. So let's see. So it looks like we've got that. Yes. So we'll just call this like, yeah, we'll just go R1, R2, R3, R4, R5, R6. This is a nasty one, R7 and R8. I don't see us doing a question like this, like word for word on the quiz, but this is great practice in terms of overall reduction. So let's kind of take a look here. So
Should we perhaps label some nodes?
that's what I was thinking right there. Okay, so we'll do A right here. B, 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 C, C. And then I'm gonna say right here, D, E, E, F, G. Wow. That's like half of the alphabet right there. Holy shit. All right, anyway.
D should be A.
D should be A. Oh yeah, you could start it here too. Yeah, it's
What G and A are?
oh, I thought you said D. Oh yeah, you're right. A. Okay. Woo. So here's let's see. So R1 and R8, those are in series. The reason I know that is because, well, number one, they have one shared node, but the other thing is that if I send a current through here, it's the same current that comes out of R1. Does that make sense there?
There's nothing obstructing it. It just goes.
Yeah, there's nothing
Boom, boom.
obstructing. There's no branches. It doesn't go anywhere else. And even I'll do you one better. Oh shoot, I didn't know that would delete the whole thing. Okay. Even better, I'll do you one better. If we had a resistor in here, we called it RB, you would say these three resistors are in series. Right? Just because it's the same current flowing through all of them, right? For example, I can't really say the same thing about R3 and R4 because if I send a current through here, this current will split that way and this way. See?
So we're looking for the forks basically
Exactly.
that
So
make it
with
not a series.
with series, there's no forks. It shares the same current, right? And so that's why just sharing a node is not enough because R3 and R4 here, they share node B. But because the current splits, that negates the fact that
Oh shit. Okay.
right?
Even if that split is a short circuit though, even though this isn't right because you have R1 at the way end. Or is
No,
it a short circuit?
think of this like this. Okay, now I'm gonna purposefully erase this whole thing. Imagine this. This is R8 or 1. Right? This is also node B right here. This is node F. You have something here in the middle, technically, but this right here is the same circuit. I just moved the resistors a little closer together. You see?
Mhm.
So these resistors here, they're sharing the same current, meaning I can combine these into just saying, hey, this is R8 plus 1. That's a series combination.
Fair.
Let's see what else we can combine here. So we have B, C, splits. Now, here's my. Oh man, I don't. Let's see. This is my second assumption here. So imagine this, right? Now I'm looking at R2 and R3 here. I'm seeing that they both. Imagine if I pinched C together, right? Let's just do like a quick drawing of that, right? Resistor. Imagine if it went to like 1 point. And then out of this, we had. Maybe. Resistor, resistor. And then this went to R4.
Why does
But
it say
then-
R4 equals 0? At
What the
the
hell?
very in blue.
Yeah. So here's how I'm gonna. Oh.
So does that mean it's just that is part of like a short circuit thing? Like it's just
That's
it's
what
just
I'm thinking.
wire.
I'm thinking if R4 is equal to 0, that's just a short circuit like that. Okay, that changes things. Because we have that. But then this also goes down. So if that's a short circuit. So this is R2, this is R3, this is R5, this is is that 7? 7 in the middle. And then this end is gonna come out here like this. And then this is all like that. I don't like how
And
I
then
don't
how
like
about
how I'm drawing this.
R6?
Yeah, R6. This is. I'm gonna redraw this. Let's see. And then this is all gonna go. Does that make sense there like that, how I drew this? This is R5. So
Uh,
this is all node B right here. And one thing that's gonna change is there's now no node E. This is all B here. Right? So then I have B. So this is B. And then this is gonna go, this is node F here, which this carries. Does that make sense there, maybe? And then this is 8 plus 1 right here. So what I'm thinking is, does this make sense? I feel like this was like really fucking nasty. Like just the way
I
this one worked out.
personally prefer the previous circuit that we have.
Yeah.
But
Okay.
that's just like my own visual preference. Like I don't.
Okay, yeah, no, visually this is atrocious here. So let's move this over to the side. Let's just put that over there. So here's what we'll keep working with this one. So here's what I'm saying. I'm seeing, check it out. I'm seeing we have current flowing through here. Now look at this. This is all node C here, right? So I see this is all one shared like this. If there was a voltage, this is all like voltage whatever. This is voltage Y, right? What I'm seeing though is that I'm seeing one shared node here between R3, R2, and R5. And I'm seeing one shared node out here. One shared node out here. Like that.
Mhm.
So
So are R3 and R2 in parallel with each other as well as R5?
yep, that's exactly what I was getting at. So with these, draw. There we go. Boom. So with these, let's see, how can I redraw this so it's like plus minus that, and then we could say, I might need to move this down a little more actually. So we're gonna say R7. We're gonna make another one. This is gonna be R2, R3, R5. And then we're gonna have this loop around like that. And then this is gonna, so this is all node B up here. And then this is gonna come out. Oh. Did my laptop lose connection?
Yes.
Oh, snap. Okay, hold on, let's try this again. Okay, can you guys see my screen here?
Mm-hmm.
Okay. So I see this is R of 8 plus 7, R7. This is going to come out and around. Squiggly, R6. Okay, so I see that. That's good. So there is, there's a few ways we can draw this. I'm going to draw this like this. I'm going to move the R8 plus 1. That's a 1, not a 7. To the right hand side. Right? So I'm going to go like this. And I'm going to do two steps in one. I'm going to combine these two resistors in series, and I'm going to move R8 plus 1 to the right hand side. So we're going to have a resistor here. And then we're going to have R8 plus 1. And then we're going to have R6 over here. Because, this is all node B. This is node I don't know, A, C, D, like this, maybe. That's all over the place. So this resistor here is going to be R7 plus R2, R3, and then I ran out of room, R5. Does that move make sense?
Yes.
Okay. Now, we're going to combine R8 plus 1 and R6 are in parallel, but they're not in parallel with this resistor here. The reason being because let's look at our little, come on, man. Let's look at our little current rule that happens again, right? If I send current through this resistor, it comes out and about and it splits two ways. So it's not exactly in parallel yet.
Mm.
So plus minus. Squiggly, squiggly. This is going to be R8 plus 1, R6. And then this is all of this. I'm just going to draw an arrow like that. That's a lot to write. Now, plus minus, we're going to get R, was that 7 plus R2 parallel R3 parallel R5 plus R8 plus 1 parallel R6. And that's my equivalent resistance. Oh, R7, R5, R2, R3 plus R6 and R1. And hey, look at that. Hey, nice.
Woo.
We did it.
Okay. Alrighty, that's fair. That's refreshing, man. God dang. All right, any questions on that one?
So
No,
we
it's
really
the
did
best
just,
feeling.
we just had to drop R4.
Yeah, it looks like, yeah,
That was stupid.
that was that was very stupid, honestly. That's like a gotcha thing, like that's not even like a skill thing. It's like,
No, it's very conniving.
yeah, that's a dirty play right there. All right, though, I'd say, look, we're going out an hour and a half here already. I think we did pretty good for circuit reduction. If we don't got any questions, I think maybe we could call it here, that way we don't burn ourselves out
Say
too quick.
less.
Sounds good.
Say
Alrighty.
less.
You
Thank
guys, I
you
hope you
so
have.
much. You've been
Yeah.
great.
That was
Of course,
fun.
no, thanks. I'm glad I could help. I'll be making another call tomorrow at 7. We're just going to do more practice questions and more. We're also going to start covering material that would be on the exam, which I think was everything up to node voltage method. So we'll be doing that.
Do you
tomorrow.
have your past exams?
I don't have past exams, but I do have all my past notes. So I have
All right.
that, and I also have like all their previous test reviews. So this was
Ooh,
my
okay.
let's see, actually it's been a while. I should probably look at this, but this was all of our previous test reviews. I think this was my cheat sheet for all of that.
Dude,
Yeah.
I didn't even know there was a cheat sheet because they don't tell us, and it was just in the syllabus. And our first quiz, like before it, someone was telling us that we were able to use it, but I saw no one take one out. So I was like, I was ashamed. I was like, I can't take out a cheat sheet. Like, what the fuck?
Yeah, no, I mean, hey, you gotta do what you gotta do. Thankfully, quiz 1 isn't too terrible, but it definitely starts getting heavy, so especially when we get down to like capacitance and inductance, that starts getting a little bit nasty. Because that's when
Okay.
we start messing around with like phasers, sinusoidal phasers was fun, but it was a lot. Like you're dealing with imaginary numbers here and stuff.
Oh shit, nice.
I don't know. It's a little all over, but hey, that's why I'm doing weekly reviews, because when you're doing this, like it gets a little dense. So
Not the pan out of everything.
Yeah, right. Honestly, this is all, look,
Bruh.
this all here is one question here. See, you see, I have it kind of separated. See,
What
and
the fuck?
your answer comes out to negative 8.74 for the phaser, whatever, you know. It's a lot.
And
It's a lot.
are they liberal with the partial credit on something like that or not really?
I was banking on that last semester, and that's why I'm here again.
Oh my god.
Oh man. Okay. Esteban
You're
is
stronger
now
than
trying to
ever.
join the call. Yeah, exactly. I'm going for an A this semester, no doubt. So
Fuck yeah.
all righty. Esteban, just so you know, we're starting to wrap up. So
Hey, what's
wanted to
up?
let you know.
Oh, damn, yo, what's good?
Hey, so I'm gonna be doing another study call tomorrow at 7
Right.
again. We're gonna cover again, we're gonna do circuit reduction, but then we're also gonna start covering material that is expected to be on the exam, which I think is everything up until but not including node voltage method.
So like basically all the way to superposition.
Yeah, basically, which that I need to practice a little more, you know.
Right. So
So yeah.
I was gonna ask like between you two, like how's it feel? How's the review felt? Like it's been good? Anything that you guys need to brush up on or
Well, I did circuit reduction for tonight, but I definitely want to touch up on superposition. I think that's what I'd probably want to do the most. I think, you know.
right. Is this
So-
did you record this? Oh yeah, this is a recording.
I did, yes. So I'm gonna post it. I'll send it out. And yeah, that's basically my plan here. I'll stop sharing my screen now.
Okay.
So if we don't got any questions, I'll see you guys maybe tomorrow at 7, and then also Monday in person is what I'm gonna try to find a spot. I don't know where, but we'll figure it out. But yeah, that's my plan. All right, guys, y'all have a good night,
Alrighty.
and I'll see you
Sounds
tomorrow.
good. Peace out. Thank you.
Peace.